Hello everyone and welcome to Numerical series of Power Plant Design. Today our numerical problem is the two power station A and B supply to a system whose maximum load is 120 megawatt and minimum load is 12 megawatt during the year. The estimate cost of these stations are as follows. The cost of A station A is 120 per kilowatt plus 0.02 per kilowatt hour. Similarly, station B 115 per kilowatt plus 0.032 per kilowatt hour. If the load varies a straight line, find for the minimum cost of generation, install capacity of each plant, the annual load factor, capacity factor of each plant, the average cost production per kilowatt hour for the entire system, assuming reverse capacity of B as 12%. This is plant A and this is the plant B. The figure is load duration, and this is 120 into 10 to power 3 and this is 12 into 10 to power 3. This is X and this is Y. Now running cost of plant A is 0.028 lower. So plant A supply base load and plant B supply peak load. Let X be the maximum demand of station B and Y be the hour of the operation. This is X and this is Y. This is hour and this is load. Therefore, energy generated by station B is 1 by 2 half X into Y. So, triangle CECD similar triangle EAE. These both triangle are similar triangle. So, EC upon EA equal to CD upon AB, that is 120 minus 12 upon X. This is kilowatt, so 10 to power 3. This is 8760 by Y. Then we can get Y equal to 0.081 X. Then energy generated by station B is 1 by 2 into X into 0.081 X, that is 0.0405 X square kilowatt hour. And energy generated by plant B, station A, that is station A is this whole and minus B, so we can get the A. CDGF plus triangle EDC minus triangle EAB, and this is 12 into 10 to the power 3 into 8760 plus 1 by 2 120 minus 12 into 10 to the power 3 into 876 minus 0.041 x square. Then we can get this value for generating capacity of station A. And maximum demand for station A is 120 into 10 to the power 3 minus X kilowatt. Cost of station A, this is already mentioned in the question. So you can multiply this 120 into 10 to the power minus X, this plus 0.08 into this above value. Then this is the cost of plant A. Then you can get this equation. And another one for plant B. Do similar for plant cost of station B. Total cost equal to CA plus CB. Then we can get add both cost of A, this and this. And then we can get this equation. For minimum cost, DC upon dx equal to 0. For minimum cost, first derivative equal to 0. Then we can get minus 120 minus 2 into 1.48 into 10 to the power minus 3x plus 115 plus 2 into 131 2 into 10 to the power minus x equal to 0. Then you can get the value of x. Okay. Then you can get the value of x equal to 15 megawatt. So put this value in above equation, the value of x here. Then you can get the value of y. X is 15 megawatt and y is 1235 hours. And installed capacity of plant B, that is x plus reverse margin, that is x plus 22% of x. That is the value of x is 15. So 15 plus 22% of 15, that is 18.3 megawatt. And installed capacity of plant A is 120 minus x. So 120 minus 15 is 105. And load factor equal to average load upon maximum, that is load factor equal to average load into maximum load. So average load, annual energy generated into time. This is annual energy generated 578 point. This is for A. So put all this value, we can get 0.618. And similarly for B, put all the value, we can get the load factor of plant B. And the plant capacity of capacity factor of A, average load upon capacity, that is 0.0168. And for B, do similar for B. By simplifying this, we can get 0.058. And average cost of production per kilo, that is total cost upon total annual energy generated. So this is total cost upon a total annual energy generated. Right here all the total energy generated. Then you can get the average cost of production per hour.